So if you please join me in welcoming Dr. Sudweeks today to seminar.
Can you hear me back there, Stephen?
Yeah, I can hear you.
You can hear fine?
Yeah.
Okay, thank you. I appreciate this opportunity. We're going to focus on the topic that's on the screen here. We live in a measurement world, whether we like it or not. From the very time that babies are born, within the first 5 minutes after a baby is born, doctors do some measurements. Actually, I guess it's probably the nurses that do the measurements. And then within the first 24 hours or so, they give some more formal tests to babies. And we're able to detect problems early on and give the baby the help that it needs. And because of that, we have improved neonatal care. But there are other aspects of measurements that we encounter on a daily basis, like the measures that are shown there. Can't hardly watch the news at night without being exposed to some of those. And usually we find some of those quite helpful. You're probably more familiar with some than others. When you go to a medical doctor, you often have some measures taken. Your white blood cell count, for example, or your blood pressure. Or you find out you might have some deficiency in terms of iron or something like that. And as you get older, you might become grateful that people can measure your visual acuity and fit you with appropriate age to help you see better. That's all part of measurement in the world we live in. Here's an interesting measure that you might not be too familiar with, called the breathalyzer test. Please note that when blood passes through a person's lungs, the air causes a portion of any alcohol in the bloodstream to evaporate. So the alcohol content of a person's breath is directly proportional to the alcohol content of that individual's blood. The amount of alcohol in a person's breath that is detected by a breathalyzer is then used as a reliable indicator of the alcohol content that that person has consumed. That's a simple situation. We don't really measure how much alcohol they consume. We measure a proxy or an indicator of that. But in the world we live in, things aren't quite, in terms of measurements, education and psychology, we don't usually have such direct measures. Now, I want to emphasize this mistake that we often make. When we talk about measurement, we act as if we're measuring some object or some event or some organism. I've given you examples of each of those categories up there. You can see examples of objects on the left and examples of organisms on the right and events in the middle. But we don't really measure objects or events or organisms. Instead, what gets measured is a definable attribute or property of the object or event or the organism. For example, in that list of objects I had, one of the examples was a house. Well, we don't measure houses. We measure one or more attributes of a house, like its amount of living space. We measure that in square footage. Or sometimes we just get a crude measure by measuring the number, counting the number of bedrooms or the number of bathrooms. Seems like in today's world, we might get a better measure if we counted the number of garages instead. But that's a different property. Well, we can also measure how far the house is set back from the nearest street, or we can look at its appraised market value, or its assessed tax evaluation, or even its exposure to radon gas. Those are all different properties of houses that we sometimes measure. Now please note, each of those attributes is a characteristic that most houses generally possess, but they have that property in different degrees or amounts or magnitudes. So it varies from house to house, and one way we differentiate among the members of the category we call house is by measuring those different properties. Here's another example. We don't measure persons. We measure some attribute or characteristic of the person, such as one of those examples that are listed there, like their blood pressure, or their attitude towards gun control, or their self-efficacy towards singing in public or giving a public speech. I have fairly high self-efficacy towards my ability to give a public speech, but I don't have very high self-efficacy about singing in public, for example. Well, those are different properties that we can measure. We might measure their creativity or their shyness. So we don't measure people, we measure properties of people. And we need to be very clear about what the property is we're trying to measure, lest we measure something different than what we think we are. Now, many of the attributes or properties or characteristics that scholars attempt to measure are abstract. They're not directly measurable. I've given you some examples there, like phonemic awareness or creativity. Some people claim they have test anxiety. Well, there are measures of test anxiety. There are measures of achievement motivation, measures of metacognitive awareness, and self-regulated learning. Those are all different properties of humans, but most of them are not directly observable. And yet, they're presumed to exist. We act as if they exist. Sometime go to a public park in the summer and talk to the mothers there that are watching their children, and you'll see mothers talking about these different constructs, different abstractions that differentiate the kids. Some of them, they might say, well, Johnny's aggressive, or those Susie's a little withdrawn and shy. Well, those are examples of latent traits. Now, the physical sciences have latent traits as well. Can you think of an example? Think of one that you learned about probably before you were a third grader. Ever heard of gravity? Gravity is not a directly observable characteristic of objects or planets, for example, but it's an example of a latent trait in the physical sciences. There are others too, like electromagnetic force. They're not directly observable. Sometimes they're hard to define. Kind of hard to measure a property unless you can clearly define it.
Dr. Sudweeks?
Yeah.
Ben in the chat is asking if mass is considered a latent trait.
I couldn't hear you.
Is mass one of these latent traits you're talking about?
Mathematical reasoning ability would be.
But mass of an object?
Oh, the mass.
Yes.
No, I'd say mass is, well, probably is a latent trait.
What about voltage?
Voltage is too. Voltage is another good example. So is amperes and current, for example. Thanks for asking. Okay. So even those abstract concepts are not directly observable. They're presumed to exist, and they're presumed to influence the way people talk and act and behave. Collectively, they're called latent traits. But since they're not directly observable, we have to infer them from some manifest behavior that is observable, for example. Now, the first step in developing a valid measure of a latent trait is to clearly define what that characteristic is and how it differs from related attributes or traits. For example, if you're going to measure spirituality, you might want to be careful to define it differently than religiosity. those are probably not synonymous traits. Both latent traits, but they're not the same thing. So the first step involves clearly thinking about how the targeted trait is likely to manifest itself and what you're willing to accept as evidence of how it varies from one person to another. Now, in our attempts to create measures, we often have to use qualitative methods to help us develop quantitative measures. For example, it's very helpful to interview people. It's very helpful to observe them and the way they behave. Sometimes we use focus groups. So qualitative methods are very helpful in developing some of our quantitative measures. It's also helpful to get into the literature, the previous work that's been done, so that you're not reinventing a flat tire. Now, unless you do that, you're going to have a hard time determining whether the scores you get measure what it is that they were supposed to measure, unless you have a clear definition of what that trait is. And you also need to be clear about what kind of purposes you want the measurements to serve, how you're going to use them, and what kind of decisions you want them to inform. Now, please note the point here. We don't usually measure for the sake of measuring. We collect measurements to serve some other purpose. It might be to help us do research. It might be to help us conduct a program evaluation. It might be because policy makers want to be informed. We might want to help a student know what the student's strengths and weaknesses are, where they need to improve. We might want to give feedback to a teacher. Well, all of those are examples of the fact that measurement is not an end in and of itself, but it's something we use for other purposes. Now, sometimes I hear about learning sciences. Some universities have programs in the learning sciences. Well, the very idea of having a learning science presupposes that we have available to us valid and reliable measures. I don't know whether we'll ever be successful in really developing learning sciences, but I'm quite confident that we will not unless we can develop appropriate measures that help us in that regard. Now, I talked about latent traits a few minutes ago.
Dr. Sudweeks,
Can I interrupt you for just a second? I think your microphone is dead. Have this.
Dr. Answer, can you hear me?
Is that here?
Thank you. So, in order to measure latent traits, we usually have to define a series of indicator behaviors that we think are likely to be manifestations of the targeted trait. Any one of those indicators by itself will generally be insufficient evidence. I spoke about breathalyzer tests a few minutes ago. That one measure of the alcohol content of a person's breath is a rather reliable and dependable indicator of whether they're inebriated or not. But that's a unique situation. In the social sciences, we usually can't rely on one single indicator of a latent trait. So we try to find multiple indicators that are correlated and together will provide us with a composite measure of that trait. Factor analysis and item response theory both provide ways to help us find out how well they function. I'm going to talk about both of those in a few minutes. But first, I want to back up and remind you of what classical test theory is. The idea of classical test theory grew out of the work of Charles Spearman, a British statistician, over 100 years ago, about 1904. The first published paper was published, and it was more formally developed in the 40s and the 50s here in America. But the basic idea underlying classical test theory is that whenever you get a test score, I'm going to call that an obtained score for an individual person, that score is presumed to be a composite that's made up of two components. The person's true score, which is a latent variable, and the person's error score. So on the left-hand side, that X represents the obtained score. And notice it's a sum of two parts, the person's true score and error. And the idea here is, whenever you administer a test, you should think of the scores that people get as being fallible, because they're influenced by not only the person's true score, but also by the error. The question is not, is there error? The question is, how much error is there in the scores? Oops, I'm going the wrong way. So here's an example. On the left-hand side, the left-hand column, you see 5 names. Each of those persons has an obtained score. Sadie has a 91, Sally has a 78, Sarah has an 81, Sherman has a 71. And each of them has a true score. And in the right-hand column, you can see the error. The error is the discrepancy, the difference between the person's true score and their obtained score. Now, please note, Sadie's true score is an overestimate. Pardon me, Sadie's observed score is an overestimate of her true score. The reverse is true for Stanley, and the reverse is true for Sherman. Classical test theory is based on the assumption that those error scores are random and that they will average to 0 across persons. Okay? Now, if they don't average to 0, that means there's some systematic error, and we have a validity problem. Classical test theory is really a theory of reliability, and it acknowledges that any time you administer a test, the score you get is subject to some error. The question is how much. Now, the beautiful thing about classical test theory and some of its antecedents, pardon me, some of its predecessors, is that we can quantify the amount of error. And we can use that to qualify the way we interpret the scores. Most of my students, by the way, claim that when they get a test, oh, well, there's error. My true score is underestimated. Well, remember, this is a random thing. So if we tested one person repeatedly, so notice the X on the left side of each of those formulas. If we tested one person repeatedly, their obtained scores will vary from test to test, but their true score will not. So down at the bottom, please note, they get a different obtained score each time. Hopefully they don't vary very much. but every one of them is only a fallible estimate of their true score. And we need to keep that in mind. So test scores are fallible. The question is, how fallible are they? Now, let me ask you to do some thinking here. What are some reasons you can think of why a person's test score would vary if you tested the same person repeatedly and they didn't have any fatigue, they didn't get tired, and they didn't learn from taking the test? Why might their scores likely vary from one test occasion to the other, given the same test on multiple occasions? Why would their score likely vary? Well, I've given you 5 categories there. That should prompt you a little bit.
We have a comment in the chat from Ben who suggests that traumatic events can impact a
Let's hear it.
person. Traumatic events.
So sometimes people experience traumatic events between one testing occasion or another. Maybe they got in a car wreck on their way home, or maybe when they got home, they found that somebody was sick or ill or passed away or something, or other kinds of traumatic events that intervene between the test occasions. That's a good example.
If they felt like they did well on the first test, then they might do better on the second test because they have more confidence. Whereas if they felt like they did bad on the first test, their second score might go down as well.
Their motivation might change, yeah. So look here. First, changes in the person's health or their motivation or their degree of fatigue or their luck in guessing. All of those are changes inside the person. But the next category has to do with changes in the way the test was administered. Like how much time was given or how the instructions or what. Maybe there was a lawnmower running outside that was distracting or something. And then maybe the trait itself changed over time. Or maybe a different person did the scoring. Or the person was more tired one time when they were doing the scoring. All of those would influence it. And then the last category has to do with the fact that we might sometimes use different questions one day than we used the day before. We might change. They might be questions designed to measure the same trait, but they might vary in difficulty or familiarity to the student. Now, all of those are reasons why we shouldn't be surprised if a person gets a different score when we test them repeatedly from one time to another. But let me ask you to give some thought now. Of those 5 categories, where did I go? Here we go. How many of those are based on factors that are external to the test itself? Rachel says 5. I would disagree on only 1. The last one has to do with internal characteristics of the test. We might change the questions from one test. But the others are all factors external to the test. So what's the significance of that? Remember I said we can estimate how much error there are in test scores? Well, one way to think of reliability is the absence of error. The less error, the more reliable the scores. But I've just pointed out to you a number of reasons why the scores are likely to vary. Most of those are external to the test, but they affect the scores. So reliability is not a characteristic of the test itself. And yet, hardly a week goes by that I don't hear students or professors in this college talking about, well, that test has a reliability of 0.62 or 0.78. The testing instrument is not what is reliable or unreliable. Reliability is a property of the scores, because that's how we compute the reliabilities from the scores, and because the scores are what are susceptible to error. You understand the point I'm trying to make? So don't talk about a test as being reliable or unreliable. Talk about reliability as being a property of the scores. Now, here's one way, this is probably the most generic way to define the reliability of a set of scores. It refers to the degree of consistency in the measurements obtained from replications. If you gave the same test over and over, you'd be replicating it. The question is, how consistent are those scores for a given person? And then you aggregate that across people. You might have seen this visual before. This comes from a book by Norm Gronlund. I think it's Dr. Davies uses a current edition of this book. It's about 11th or the 12th edition. I studied that book when I was in graduate school, and it had this picture in it. Please note, this is intended to represent the results of 3 target shooters. I don't know whether they're shooting guns or shooting a bow and arrow or something else, but they're shooting at a target. What's the difference in those 3 situations?
Level of accuracy.
The level of accuracy, yes?
Well, two of them
Microphone,
are reliable.
Thank you.
Two of them are reliable in their consistency,
So which 2 are reliable?
the left and the right.
So here we have a very consistent shooter, but he's off target, but he's consistent. My wife says I'm very predictable, I'm just wrong. She's accusing me of being like this, consistent but off target. So this one would be reliable but not valid. This one would be reliable because it's consistent and it's on target, so it's reliable and valid. But this one is all over the place. That one's neither reliable nor valid. So how do you get the situation on the right? That's an example of systematic error. The one in the middle is an example of random error. There's no reliability nor validity. But when we have systematic error, we get the situation on the right. It's reliable, but not valid. The scores are reliable, but not valid. That's analogous to stepping into your bathroom and stepping on the bathroom scale and finding out that every time you weigh, the scale weight, this reading on the scale is 4 pounds heavier than you really are. That would be systematic error. A story that I used to tell my students. When I was a young man, I grew up in the little town of Nephi, by the way. And when I was a high school student, I purchased a car. And my mother would often borrow my car without asking. And on several occasions, she got a little upset with me because she ran out of gas. Why didn't you tell me it was empty? Well, you didn't ask. That was in the days when gas cost 29 cents a gallon, by the way. And I didn't have enough money to keep it filled up. My car had a gas gauge. When it read a quarter tank, it was empty. I knew that. It was systematically off. It was dependable. Whenever it got to a quarter of a tank, you knew it was empty, but my mother didn't. But if she would have asked, I would have told her. Well, that's an example of systematic error. The measures were reliable, they were just invalid. So when we're making a test, we ought to do what we can to avoid any kind of systematic error. Now, I meant to bring a copy of this book. The book I'm talking about, it has the title that's shown there. It's in about its 6th or 7th edition. It's published by the joint efforts, collaborative efforts of the American Educational Research Association and the American Psychological Association and the National Council for Measurement in Education. And it specifies the standards that should be used in judging the quality of educational and psychological measurements. If you're going to do much in this area, you need to be familiar with that book. You can find a copy at the library, you can find copies online, and if you need to, you can borrow mine. I want you to know that it exists. So we've already talked about that point. Now, according to classical test theory, you can estimate the reliability of the scores and get a number, a single number, that indicates how reliable they are. We call that a reliability coefficient. The most widely, and by the way, it's usually a number between, it has to be between 0 and 1. Hopefully it would always be above 0.5, and ideally it would be much higher, like 0.8 or 0.9. But that single number is called the reliability coefficient. The most widely used coefficient for doing this is named after a man by the name of Lee Kronbach, published in a paper in 1951. It provides an estimate of the internal consistency of the scores. It has the advantage that you don't have to give the test more than once. That's an old way of doing it. And you don't have to use parallel forms. You can just give one test on one occasion. And it's available in most software. But even though it is the most widely used reliability coefficient by far, scholars now know that it has serious limitations. Those are shown, I think, here on the next slide. This one, I've got a slide out of place there. So that coefficient is based on 3 assumptions. First, that all the items measure the same trait. Secondly, that their factor loadings are not statistically different. In other words, there's no significant difference between them. And third, that there are no correlated errors. Kronbach's alpha is so easy to use that people rarely test those assumptions. But if those assumptions are not met, Kronbach's alpha will either underestimate or overestimate, depending on which assumption is violated. So if you're a knowledgeable person about educational psychological measurement, when you see a research report that says, well, we used Kronbach's alpha and the reliability was 0.84, you ought to ask yourself, did they test those assumptions? And if they didn't, then you wouldn't put much credibility in that coefficient. Now, there are some alternatives that you can use that don't have those same limitations. One is called McDonald's coefficient omega. That one is useful if the second assumption is met as well as the first one. Raykov's rho coefficient is useful if the third assumption is violated. Both of those assume unidimensionality, just like Kronbach's did. But I want you to know that they exist. and they should be used if the corresponding assumption is violated. Now, I also want you to know that in the last 70 years, classical test theory has been extended and improved upon by these three theories that are shown here: generalizability theory, item response theory, and congeneric test theory. They don't replace classical test theory, they just extend it and improve on it. Congeneric test theory allows us to address some validity questions by using factor analysis. It allows us to answer, to find out if the test measures, is it really unidimensional, or does it measure more than one construct, or more than one latent trait? And which items, if any, do not load on any of those intended traits? And are there some items that are so ambiguous that they load on more than one? And most importantly, do we have one trait or two or three or four? Well, congeneric test theory allows us to use factor analysis, either exploratory or confirmatory or both, to answer those kind of questions. Here's an example of confirmatory factor analysis. The rectangles at the bottom each represent a test item. And you can see that the four on the left supposedly measure whether a person is lying or not. And then we have some items that presumably measure cheating. And then we have some items that presumably measure stealing. And those three factors are all presumed to be manifestations of honesty. So this would be a second order factor. If we're making a test to measure a trait like honesty, or one of those subtraits, then we want to have multiple items to measure each of those subtraits, and we want to submit the results after we've collected data to a factor analysis, and that would help us know, it would give us evidence of whether or not we have construct validity. Now, I also mentioned a new theory called generalizability theory. This particular example comes from a study we did here on campus years ago, where we were studying the writing ability of sophomores by having them respond to essays. Well, it turns out you have to rate the quality of the essays, and so the scores that you get are somewhat dependent upon the raters, and also dependent upon how many essays. This tells us, for example, if you only use one essay, you get these results depending upon how many raters you average. If you use 2 essays, you get this result, and 3 essays and 4 essays. So the reliability here is not a single number. It's a function that varies as a function of the number of essays and the number of raters that you use. So this gives us much more information than we used to get through traditional estimates of reliability. Now, I talked about item response theory. We offer a course on item response theory, and sometimes we offer an advanced course in it. There are some very important practical applications of this theory that grew out of work done back in the 60s and 70s. You can see 6 different practical applications there. We can do item analysis that's not dependent upon the sample of examinees. And we can get estimates of people that are not dependent upon the sample of items. We can also estimate the precision of the examinee's scores at varying levels. In classical test theory, you get one reliability estimate, like 0.82 or 0.92 or 0.76, and that's presumed to be the scores are equally reliable regardless of people's ability. Well, that's probably not true. In fact, it's an oversimplification. I'll show you in a minute an example where we can estimate reliability at different levels of ability. But with item response theory, we can also create adaptive tests where we don't have to give everybody a test that's 50 items long or 40 items long. We can shorten the test by focusing on items that are close to that person's ability. They don't have to take all the items that are easy or all the items that are hard. We can focus on items that are close to their ability level and shorten the test and get a more precise estimate. We do that using what's called computer adaptive tests, or even better today, multi-stage adaptive tests. Number 4 is very important because it allows us to detect items that are potentially biased against subgroups. You know that we live in a litigious society where people sometimes file lawsuits. Sometimes they file lawsuits against employers who use a test to decide who to hire, and they file lawsuits against colleges who use an admissions test or a licensure test because they claim the test is biased. Well, item response theory is one way, a very important way, to detect items that are biased against blacks or against females or against some other subgroup. We also can equate forms. An example of that would be the mathematics department here at BYU. Routinely, when they test their Math 112 students, they make up 5 or 6 forms of the test that they send at the testing center. So when one student goes, they get Form A, and their friend gets Form C, and somebody else gets Form D. Well, that all assumes that those tests are equally difficult. Very hard to write equally difficult tests. In fact, it's usually not successful, but you can equate the scores using item response theory. And you can also set standards for determining levels of proficiency. All of those are examples of item response theory. Question? Okay. Now, I said a minute ago that using item response theory, we can get a better indication of the reliability of a test. Instead of getting a single number, like 0.82, and acting as if the test is equally reliable or the scores are equally reliable for people at all ability levels, using item response theory, you get a curve like this called the test information function. This axis over here is called information, which really means precision. How precise are the ability estimates we get for people, or the trait, whatever trait we're trying to measure? How precise are those scores? Well, this graph says the precision is very low for people in low ability areas, and it's very low for high ability people. We get most precision in the middle here. That might be okay unless we really want to get better estimates of the high ability and low ability people. If that's the case, then we need to add more difficult items over here that will increase the precision over here, and we need to add some easy items that would increase the precision over here. Also, suppose this test were being used to decide who gets licensed or not, or who gets admitted or not to a college, or who is decided as passing and failing the test. If we have the cut score right here, we want our reliability function to be at its peak right above that cut score. This shows that that wouldn't work well for this particular test. If that's where our cut score should be, we need to add more items that will give us more precision in this range of the ability level. You can't do that with classical test theory. item response theory provides a way to find that out and respond to it.
4 minutes, Dr.
Okay, thank you. I want to end with this idea. Psychologists typically refer to tests as being instruments. But that word instrument is just a glorified name for a tool or an implement. In one sense, it's appropriate because it implies that the tool is designed to serve a particular purpose, and that's always true, and we need to remember that and use it only for that purpose. In another sense, to call a test an instrument is maybe overstating it because it implies that it's designed for really delicate scientific kind of work. And most of our tests may not satisfy that need. But we need to remember that all tests are tools designed to get a sample and examine his behavior and to enable us to make some measurement as a result. But like any other tool, tests can be misused. Sometimes we use a screwdriver when we really need a hammer. Or we use a hacksaw for cutting a board. Well, that's not what hacksaws are designed for. Tests are tools, and they ought to be used only for the purpose for which they're designed. And they shouldn't be misused. Now, I've given you here some guidelines for using tests responsibly. You need to be careful when you select or create a test. If you can't select an off-the-shelf test, then you have to make one. But making a good test is not something you do in 30 minutes or even a day. Making a good test takes effort. Clearly defining what the trait is, writing good items, trying them out, revising them, deleting some, keeping only the ones that are working, then getting a reliability estimate and checking for validity. Now, you might be familiar with this proverb, measure twice, cut once. That's what classical test theory says. There's a Russian version of that that says measure 7 times, and then cut once. When you measure twice, take the average of those two, because that's going to be more reliable than either one of the 7 ones. And better yet, take the Russian approach. What all this means is we should never make an important decision based on a single test score. If we really want to measure people, let's get their responses to multiple tests and not just one. Now, what I didn't talk about yet is the importance of measuring change. Historically, measurement people were very discouraged about trying to measure change, even a test retest. Lee Kromack has a famous article in the 1970s where he says, don't even think of the question that way. Reword the question so you're not trying to measure change. Well, that's kind of a cop-out. Because as educators, we're about trying to change people, trying to produce change. That's what we have instruction for, is to change people. Well, in today's world, we can use growth models and growth trajectories and show differences in the way people change. In this case, we've got 6 people. They start close together. They spread out as they learn. Some of them learn at steeper rates than others. In this case, we used a simple one where they're linear. All the growth trajectories are straight lines, but they could well be curved. Modern approaches permit you to get at that. Now let me just close by that slide right there. There are a series of measurement courses that are available in the instructional psychology department. Dr. Davies teaches that 652 course. Sometimes Dr. Larson teaches 752, sometimes I do. We also have those other courses there. if you're interested in learning